The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
As I said, our next speaker is listed as Mark Burry of BASF, but unfortunately he couldn't make it here today, so Brad Violetta, also of BASF, has agreed to step in and give this presentation, which I'm going to find in just a second. And with that, would you please help me welcome Brad to the stage.
Thanks, Dave. As chairman of ACI 212 and also a co-moderator, it is one of my roles and responsibilities to fill in for people when they don't show up. And so I'm honored to do that twice today, actually. And it was as a result of the tornadoes last night, or the weather that keeps going on. So I will try to do justice to this presentation. It is chemical admixtures and advanced methodologies to produce and quantify sustainable concrete. It was prepared by Mark Berry and David Green of BASF. And the presentation definitely spends most of its time talking about the quantification of the sustainable impact of different concrete mix designs. So when we look at the mega trends in the industry today, most of the discussion is around two subjects, the economy and sustainability. And these issues will continue to challenge and shape our concrete industry in the future. And so as concrete producers, technicians, suppliers, we have two main goals in producing concrete, and that is to optimize the mix economics and performance. Make good concrete, make it inexpensively, but also it's important for us to lower the environmental impact of concrete. And so the old way was simply, just take regular, vanilla concrete, cement, sandstone, water, and some admixtures, mix it for 5 minutes, deliver it to a job site, and place it. And then you end up with cubic yard or 4,000 pounds of concrete. The only problem is if we follow that recipe, there's a cash and a carbon or a environmental cost to doing that. And there's advanced concrete technologies that are moving us to more sophisticated and lower ecological impact mix designs. And we're able to do this through proportioning expertise, the use of different types of recycled materials than we've used in the past, special PCE admixtures, and workability retention. And it's depicted on this slide, which is, if the world that we used to live in, was, concrete that was expensive to produce, but low to moderate durability or low to moderate workability or high porosity, somewhere in this world, we can move up into this area, which is lower cost concrete with better workability, better durability, and lower porosity. And the thought of maybe doing that in the past was a little bit unthinkable. I mean, how can we make concrete better and cheaper, and in the end also with a lower environmental impact? And so ERA started to talk about this a little bit, and that's the replacements of large amounts of Portland cement with different ingredients and whether they're things that we're typically used to replacing Portland cement with, like fly ash and slag, or is it some more exotic things and combinations of things like maybe out-of-spec silica fume or metakaolin or cement kiln dust or even limestone fines or aggregate fines. I mean, mixes can be proportioned using all of those ingredients, and it isn't one magic recipe. There isn't a recipe that fits all. That when we're looking at designing mixes for performance and low environmental impact, you have to look at the mixes individually, and you have to just determine, what's the type of mix, what's the workability and engineering properties, and then look at what region are we in and what are the available materials. Is there fly ash? Is there metakaolin? Is there silica fume? Is there limestone fines, for instance? And then determine the reactivity of these materials and match them with the right novel chemistry. And I think Era did a great job this morning talking about some of the novel chemistries, and the molecules of these PCEs, but to match the mix design with the reactivity levels of the recycled materials with the right chemicals, and then use expertise in gradations and custom software and proportion expertise to come up with specific optimized concrete mix designs that are cash and carbon costs are minimized. So you start to hear about 50, 60, 70% replacement of the Portland cement with combinations of these different materials. And so a question comes to mind, and that is, okay, we know how to measure performance of concrete, right? We know how to measure compressive strength and modulus elasticity and setting time, and so we can make sure that these mixes that are containing high amounts of recycled material perform from an environmental standpoint. But how are we sure, and how do we measure the environmental impact of these different concrete mix designs? And so when doing so, you really need to take into account three different pillars. And those pillars are economy. Is it sustainably less expensive? Ecology, is it a lower environmental impact? And then third is social responsibility. Is it just the right thing to do? And so when measuring the environmental impact of concrete, you should look at all three of these pillars. And so we always hear about buzzwords in the industry, in our society, lower CO2 emissions, lower carbon footprint. We hear those all the time, but I don't think we always understand what that means. And so in this case, an analogy is a more fuel-efficient car. So if you make a car lighter and you make a car more aerodynamic and you make it lower rolling resistance and have a battery-assisted hybrid and a lower air conditioning requirements, that sounds great, right? Let's party. It's a great achievement. But really, you need to go back, and this is just to make a point related to concrete. You need to go back and look at what have you really accomplished. If it's lighter because of certain plastics, or aerodynamic because of different alloy systems or innovative rubbers, a supplemental engine or reflective paint, those things should be considered in an environmental impact of a car. So who knows? And we're not saying this is the case. We're just saying that you really don't know how more environmentally sound this car is until you go back and quantify, well, is there more oil being used because of the plastic? Is it higher energy because of the alloys? Right down the list, are we using land to mine the rubber, heavy metal disposal, or toxic? And the whole point is that you can't tell on the surface whether something is environmentally sound or if these are a good sustainable choice. So now the analogy moves towards concrete, and so we keep hearing recurring themes, reduce cement content, more supplemental cementitious materials, and use recycled concrete. And so in these mixes, which would be more sustainable? So if you had a mix, and by sustainable we mean lower impact on the environment, a good impact on sustainable construction. So if you had a mix with 517 pounds of cement or 564, most people say, well, more cement, that one is probably less sustainable. Well, maybe that is and maybe it isn't. Maybe it depends on how far the cement is coming. If the cement is coming in from China, maybe that mix isn't more environmental. And so the author goes through several examples of mixes that you would think you would know would have a lower environmental impact just by the experience we've had so far. And for instance, in this case, one would say, well, of course, a fly ash mix, reducing the cement content would be more environmental friendly. Well, that's only the case if fly ash is readily available and you're not shipping it in all the way across the country, and you're not taking into consideration all of those aspects. And it's the same with recycled concrete. Maybe some has no recycled concrete, some has 20%. It depends on the recycler efficiency and all that. So the point is that how does one know which one is more sustainable? And the reason you want to know it is because we want to be able to quantify the environmental impact of concrete. And everybody these days is talking about green. This is green, that's green, everything's green. But one method of keeping from greenwashing the industry is through measurement, quantification. And so the solution to the solution to possibly greenwashing is measuring. It's quantifying the environmental impact of our concrete. And there are eco-efficiency analysis available where that can be done. So let's talk about eco-efficiency analysis. Eco-efficiency analysis is a life cycle methodology for comparing the ecological and economic influences of an alternative. So you compare one or several alternatives to some type of a reference. And it could be a product, it could be baby diapers or concrete, it could be curing compounds versus steam curing, it could be technologies, automobiles versus motorcycles. And there are methodologies that help us define how to do some of these things through ISO, NSF, and TÜV. And so as a matter of fact, there is an NSF protocol, it's P352, and it's validation and verification of eco-efficiency analysis. And it does a few things. One, it considers the methodology. It describes the methodology for developing an evaluation at the product level. So again, it could be concrete, it could be diapers, but it describes how to follow that. And then it relies on life cycle analysis standards that are developed by ISO. And life cycle analysis in this case is taking all of the environmental burden of the different ingredients through the whole life cycle of a creation of a product. I'll show you that for concrete in a minute. And this NSF protocol is divided into two parts. The first one is validation of a methodology. So it describes how to do the methodology, but it also will they will also validate actual studies. So if somebody went to this NSF protocol, they could read about how to do a eco-efficiency analysis for concrete and create one if they wanted to. And if somebody did create one, they can also then get NSF to then verify the actual specific study. When developing that eco-efficiency analysis using the NSF protocol, there's a process that they go through, establishing the study goals, defining the functional unit and alternatives. The unit's concrete, the alternatives will be described as this. Establish system boundaries. Is it going to measure transportation? Is it going to measure or not? Those type of boundaries. And then it will determine the economic of the life cycle segments, and then calculate costs, or it will determine the environmental inventories of all the ingredients in the concrete, and then quantify the burden, and then circulate it back into here, and so you get an environmental economic impact of the different concrete, in this case, alternatives, and you get a eco-efficiency profile that includes social and relevant factors. So let's talk more specifically about a eco-efficiency analysis, and the one that is being described here is an interactive computer program. It gathers data from different vendors, from industry associations, government database, contracted consultants, and it evaluates the environmental and economic impact of concrete ingredients based on the input. Meaning you put in your reference mix, and then you put in up to 4 different alternative mix designs, and then it will it'll quantify the environmental and economic impact for each mix compared to the reference mix, and it'll compare up to 5 different mix designs for 6 different impact areas. And so what is meant by 6 different impact areas is described here. That typically, as we said earlier, when we talk about environmental impact, 2 things people always talk about is CO2 emissions and energy. Well, there's so much more to consider, and these eco-efficiency analysis, they do that. And so, for instance, they will analyze these 6 different impact areas, including consumption of energy, which we need to do. Second is emissions, and not just air emissions, but also water emissions and solid emissions. And not only just air emissions in terms of CO2, but air emissions in terms of global warming potential, ozone depletion potential, photochemical ozone creation potential, and acidification potential. Now, look at these and remember these, because I'm not going to repeat those again. I'm going to use the acronyms for them in the future. So also, the EEAs can take into account toxicity potential, or what's the effect on these materials on human health in terms of toxicity. The second is risk potential. How dangerous are these materials in terms of accidents or occupational disease? And again, I'll show you in a minute. This is a cradle to gate analysis, so it goes all the way back to the mining of the raw material. So that's why you have to consider, the occupational and accidental physical hazard. The other one is consumption of raw materials. Are the materials that are going into our concrete, are they renewable? Or are they not? And then the last one is land use. How are we affecting land when we're either gathering these materials, mining these materials, or transporting these materials? Like, if you had to put a plant up in the middle of a Brazilian rainforest, it wouldn't do well under this category. So these are the different types of environmental impact areas that can be studied. And as I said, this is a cradle-to-gate analysis. So it begins at the mining and extraction of the raw materials, and it doesn't matter whether the raw materials are cement or aggregates or chemical admixtures or water or recycled material. It takes into account, the acquisition of those materials, the delivery of those materials, and the environmental impact of those materials to the concrete plant and to the manufacturing of the concrete. It doesn't take into account the plant or the delivery. It's assuming after that point all else is equal. The plant's still the plant and the truck fleet's still the truck fleet. So it stops. It's a cradle to gate. These eco-efficiency analysis can be conducted. They can go cradle to cradle if they're designed that way, to the use of the concrete, to the demolition of the concrete and the reuse of it. This one that we're talking about here is cradle to gate. So how these EEAs work is that there's data input, and so the producer's plant project information is put into the computer. the volume of concrete is entered, and you want to know that because you can do an eco-efficiency analysis on a plant, you know, if there's a certain amount of volume out of a plant, or you can do an eco-efficiency on a project. Then you want to include your raw material costs, your mix design information, your transportation distances, where are all the ingredients coming from, and then the computer does an environmental profile, sums the raw materials, does a calculation, and out comes a custom report. And in the case here, it's about a 22-page report. And again, basically what it does is a couple things. When it does an environmental impact analysis in those 6 areas that I keep mentioning, and here they are. And the first thing the program will do will give you a quick fingerprint of the alternatives. So this would be an example of a, let's see, 1, 2, 3, 4. You know, there's 4, 5 lines up there. So it's the, you know, one reference with 4 alternatives compared to it. And so this is a quick fingerprint, a quick snapshot of the results, and the closer the lines are normalized to 0, then the lower the impact. So in this case, if you were looking at this, whatever these mixes might be, this would be the highest risk potential. All the other alternatives would be lower. And then in this case for toxicity potential, some of them are actually lower, and the red and the yellow are about the same. And sometimes the toxicity potential could be outside of the reference. It could be worse. And so it gives you a quick view. But also, then another quick view is an EEA profile, where all of these ecological impacts are normalized into one number using societal measurements to do that. And then it's compared to the cost of the mix, the actual cost of the mix. And so you can compare these different reference mixes and alternative in terms of environmental impact and in terms of cost, which with the better for both being the farther up to the upper right. Now, these are just broad views of the results, but for each one of the environmental impact areas, there's also a very in-depth study that shows an actual quantification and a practical equivalent for your different mixes and for your compared to your reference. And I'll show you an example in a minute. But I wanted to let you know that this is just a quick snapshot. That there's the actual quantity and practical equivalent for each one of these impact areas. And so what I want to use as an example to demonstrate that is the World Trade Center. And before I go on, I want to encourage everybody in the room to stay for the entire session, because Kaz Bagnacki is going to be doing a very interesting and much more in-depth discussion on the World Trade Center and another project. And so all I want to talk about is some environmental impacts that we did, analysis that we did on this project. I encourage you to stay for Kaz's presentation. So, and if you have any questions about the World Trade Center, he would absolutely want to be the man you'd want to ask. And so, but in this case, there was a couple of different mixed designs used for the columns. It's a 12,000 and a 14,000 PSI column. It was SCC, and it's much higher now. But through the 40th floor, there was 38,000 yards. I guess it ends up being somewhere around 100 floors or something. And I know it's not called the Freedom Tower anymore. It's the Tower 1. And so, but anyway, so there was an eco-efficiency analysis conducted on Tower 1 partially the way through construction. And that's the data that's presented here. And so let me take a little minute on this graph. So as I said earlier, there's several different, the 6 different impact areas, and there's quantifications for each one of those. And so simply what was put into the eco-efficiency analysis was very simply had a reference mix of all Portland cement been used. This would have been the environmental impact of that mix design. The actual mix design, which I'm not sure what it is, but the actual mix design contained SCMs and had a much lower impact on the environment. And so how you see something like this, for example, and this is all, at this point, it's all in a per cubic yard basis. So for instance, the embodied energy, the energy to create that yard of concrete was, for instance, 833 kilowatts for the reference mix, and it was 619 for the actual mix. So there was a savings in embodied energy of 26%. And so you can go right down the columns and say, and you can see that this is the raw material consumption, 20% savings, fossil fuel consumption, 22% savings. Here's those air emissions that I asked you to memorize. The global warming potential, 42% savings. POCP, which is, that's actually smog, that's what that is, 7%. AP, which is acidification, is acid rain, 40% savings. Water emissions, 15% savings. Solid waste, 16%. And land use, 4%. And again, this has little to do with the site. It's the actual production, mining of the raw ingredients and production of the concrete. So there could be more savings on site. This is just from the production of the concrete. And so the same type of analysis then was compared to the 12,000 PSI mixes. So you're seeing, that by the actual design used in the mixes, that there was quite a bit of savings per cubic yard of concrete in both cases. Now the natural next step, of course, then would be to look at the actual, take those numbers and say, well, okay, how many yards of concrete were used in this case? And again, in this case, it wasn't the whole structure. It was a partial way through the construction of Tower 1. And so, again, all the author did was take the savings, multiply it by the number of yards, and got a total amount. And so in this case, you could see in kilowatts hours of savings, there was 1.2 million from the 4,000 PSI mix, 6.9 million for the 12,000 PSI, for a total of 8.2 million in embodied energy in kilowatt hours. And you can see it right down the line from CO2 emissions, almost 12.2 million pounds of CO2 saved. This is the acidification potential, the solid waste, and the fuel consumption. So these are the hard quantities of savings from the environmental impact. I mentioned earlier practical equivalence, and so that's what you're seeing over in this column. And I'll just go right to the total. So this savings in kilowatt hours would be the practical equivalent is the amount of energy it takes to fire up 714 typical houses for a year. So that's how you can kind of put a feeling and an understanding on how, what does 8.2 million kilowatt hours look like? Well, there you go, 714 houses for a year to power them. And then it's the same as you go down the, as you go down the list that these are all, saving, this equivalent of saving almost 7,000 acres of forests, acidification, same as 5,200 air conditioners, solid waste from 85,000 people, and barrels of oil. So again, hard quantification and then a practical equivalent. So in closing, these eco-efficiency analyses are good for internal use, internal to see how well we're doing ourselves internally with sustainability initiatives, but most importantly to quantify the ecological impact of optimized concrete mixes for community acceptance, for market acceptance of our recycled green concrete, to help position concrete as a leader in sustainable construction, to spec changes to getting projects to use some of our sustainable and innovative concrete technologies. So these programs are much more than you know, life is much more than CO2, and it's much more than lead points. It is all about, you know, full life cycle analysis of the environmental impact of our concrete. Any questions?